Okay, we'll edit that out as usual. But I think we're good now. So CS 161 Lecture 6 block ciphers. Woo! Sometimes I wonder if I have like family and they're walking on me doing that. That would be kind of embarrassing. But I think I made it this time, so we'll see. But yeah, welcome back, everyone. Today is block ciphers, which is, oh, thanks. Yeah, I'm working on all my impressions, so we'll see how many I get through this semester. Okay, so today is block ciphers and modes of operation. So before we get started, as usual, there are a couple of announcements. Homework 2 will be released immediately after we're done with this lecture. So if you're on tape delay, it should probably already be out. And because we released it a little bit late, it'll be due Wednesday, July 7th, so a week from today at 11:59 p.m. as usual. Project 1 is still out, and it's still due Tuesday, July 6th. And there are no lectures, discussions, or office hours next Monday, that should say July 5th, because of July 4th, Independence Day. So go and, I guess there might be fireworks this year, I don't know, but go out and do something fun. And we will still have discussions on Tuesday, so the discussion for that half week is still on. I think that's everything. Any questions? Sorry, I think my mic is acting up, so give me like 10 seconds and you can start. Okay, I think it's fixed now. People can still hear me, right? Yes, okay. So a quick review of what happened last time. So last time was the first cryptography lecture. So we talked about how crypto is the study of communicating securely over insecure channels. And we gave you the disclaimer that you should never try to write your own crypto based on things we teach you in this class. You should always use existing libraries that very smart people have written and tested over the years. And we talked a lot about the definitions of crypto. So what are we trying to solve? How do we solve these problems? How do we know if we have a good solution? And those definitions evolved. Alice and Bob are our heroes. They're going to send messages over an insecure channel. Eve is the attacker who's going to read messages. Mallory is the attacker who's going to modify messages. So those are our characters. Then we talked about how we want confidentiality, which means the adversary can't read our message. We want integrity, which means the adversary can't modify our messages. And we want authenticity, which means we want to be able to prove that the message came from the sender. So those are our three properties. Then we talked about how the main building block of any cryptographic scheme is a key. And we talked about how Kirchhoff's principle is a security principle that says the attacker knows everything about the system except the secret keys. And that's a good way to design crypto, because if the attacker steals our keys, all we have to do is change the keys and we're done. But if the attacker finds out something about our system that was secret, now we have to redesign our system, which is way more work. And then finally, we talked about threat models. So there are a whole bunch of different threat models, but the one we care about is chosen plaintext attack. So in this model, Eve is allowed to trick Alice into encrypting any message that Eve chooses. So those are our definitions. Then we gave you a brief history, but I think most of those were optional, so you don't have to remember Caesar cipher or Enigma or anything. But we did talk about NCPA security, which is a security property that says, even if Eve can trick Alice into encrypting messages, so even if we give Eve the power to perform chosen plaintext attacks, if Eve is given the encryption of either M0 or M1, so Eve knows that one of these two was encrypted but doesn't know which one, Eve can't distinguish which message was sent. Was it M0? Was it M1? She can't tell with probability greater than a half. So if all she can do is guess, then that means that the scheme didn't leak any information about the plaintext. So seeing the ciphertext didn't help her because she's still guessing, and that means that the scheme is NCPA secure. And to test this, we had a little game played between Eve and Alice just to make the definition, I guess, a bit more fun or intuitive. And there were a couple of edge cases to consider. So if it's an NCPA secure scheme, it can leak length, because if we wanted it to not leak length, it would be very impractical. We also said Eve is limited to a reasonable runtime. So you can't use an attack that would take the life of the solar system. A common example is Eve is limited to polynomial time algorithms, but not So exponential time algorithms are not okay. And finally, we said Eve has to have a non-negligible advantage to win. So if she wins with probability 1/2 plus 1/2 to the 128, that's basically 1/2, so it's no good. But if she wins with probability 2/3, that's non-negligible, so she can win. And then finally, we talked about our very first symmetric key encryption scheme, the one-time pad. So this scheme says Alice and Bob, well, first of all, it's symmetric encryption. So we're assuming that Alice and Bob have been blessed with a secret key from somewhere. And then we said to encrypt, you XOR with the key. To decrypt, you also XOR with the key. And because XORs cancel out, the scheme is correct. And then we said that if the key is never reused, it's perfectly secure. I think it says in CPA, but it should say perfectly secure. So the definition we used there was perfectly secure because no information was leaked. And if the key is reused, then it's not secure because Eve can learn information about the plain text. And because one-time pads take so much key material, you have to use a different key for every single message. It's really not practical in the real world unless you're a spy for whatever reason. So one-time pads, they're great. They're our first encryption scheme, but they're not practical. So today's goal is, we're still in symmetric encryption because we haven't really solved it yet, but we're going to try to solve it and create practical symmetric encryption schemes. So schemes that actually work in practice. So that's what happened last time. So today is all about block ciphers and then modes of operation. So how we chain them together to create schemes. So we'll see all this today, but since you don't know what any of this is yet, we'll just skip over this for now. I think this is from yesterday, but since we kind of ran short on time, I guess we'll bump it to today. But one side note that is worth knowing is traffic analysis and side channels. So traffic analysis is the study of analyzing who is talking to whom and when. So maybe if something is sent over the insecure channel, you can't figure out what it says because it's confidential. So if it's ciphertext, I see the ciphertext and I don't learn about the plain text. But maybe if I see the ciphertext, I learned the fact that, oh, Alice is talking to Bob today. Or if I don't see ciphertext, I might assume Alice is not talking to Bob today. So traffic analysis is analyzing not the contents of the message, but just the fact that the message is being sent. So today I know that Alice is talking to Bob, and maybe tomorrow I know that Bob is talking to Alice. So most of the schemes that we study don't actually hide who you're talking to. So if you're Eve and you see a message cross the insecure channel, you can see that it's going from Alice to Bob. And maybe you can analyze that for some information. There are also side channel attacks. So these are schemes that are secure in theory. So we can prove that they're secure with our math and in theory. But if you implement the scheme incorrectly, you leak some information about the plain text. So this is where not writing your own crypto is super important, because you can have a scheme that totally works. Someone has proven that it's in CPA secure. It's secure against everybody. But if the code that you're using to implement the scheme is just slightly wrong, you might be leaking information from your implementation. So that's really dangerous and something we'll see a couple of times. And most modern crypto systems use schemes that are secure in theory. So again, people have mathematically proven that they're secure. But because the implementation has bugs or the person who wrote it didn't know what they were doing, the side channel attacks are possible. And that's how a lot of modern systems are broken. So we'll see a lot of those in the next couple of lectures. So we have one example for you for now. And this is kind of carried over from yesterday where we were talking about spies. But sometime in the 1990s, there were some Russian spies in the US doing who knows what. If you've seen the TV series The Americans, I think it was based on this, although I haven't seen it, so you'll have to take this last word for it. And there was a number station in Cuba. So a number station is just a radio station that broadcasts some numbers back to home base. So if you're a spy and you're working on one-time pads and you encrypt something with a one-time pad, the number station will broadcast your ciphertext back to home base for you. So the spies would write their message, and then the number station in Cuba would broadcast the numbers of the ciphertext back to the home base, wherever that was. But the problem was whoever was implementing this number station had a bug. So sometimes it would broadcast all the random numbers. It would broadcast 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But sometimes people noticed that it never broadcasted 9. So it would say things like 5, 7, 2, 6, 0, but it would never say 9. And people did some research and figured out any day the radio station didn't say 9 was also a day where the spies were on vacation. So, oops, right? One-time pads are perfectly secure, and we proved it yesterday if you never reuse the key. But because the implementation of the one-time pad was not perfect, they messed up and forgot to broadcast 9 on days where the spies were on vacation. Well, now people can figure out today the spies are working and today the spies are not working. What does a vacation look like if you're a spy? That is a pretty good question. I don't know, maybe you can go sightseeing in the US, but maybe the Americans has like a filler episode where the spies just go on vacation and we can watch that together. I don't know. And so the FBI actually realized this fact and used it as part of their investigation against the spies. So that's an example of side channels. And again, the problem here was not that the algorithm was insecure, because we showed that the algorithm is secure, but the implementation of the algorithm was not secure, and that leaked some information about the spies. Okay, so that was our leftover topic from yesterday, and we'll see it a couple of times across the crypto unit. But today is all about block ciphers. So the first thing we have to do is, well, I can show you where it is. So we're still in symmetric key. So we're still assuming that Alice and Bob have a secret key, and we're still not worrying about how it's done. And we're still looking for confidentiality. So we're still not worrying about integrity or authentication yet. Those will come tomorrow. So the first thing we have to do is define block ciphers. So what are they? So a block cipher is just a function or an encryption and decryption algorithm, and it works on fixed size blocks of bits. So what we mean by that is that the input has to be a fixed length. So for example, the encryption scheme, it takes in 2 inputs. It takes in the k-bit key k, and then it takes in an n-bit plaintext m. So these are fixed. So you can't give it a longer key or a shorter key. You also can't give it a longer plaintext or a shorter plaintext. It has to be n bits every single time. And then it runs through the encryption algorithm, and the output is an n-bit ciphertext C. So n bits go in, and then n bits come out. And sometimes you see this if you're familiar with mathematical notation. And the decryption algorithm is basically the opposite. So again, I take the key, which is k bits long, and I take the ciphertext, which is n bits long, and I output a plaintext, which is n bits long. And again, the notation is the same thing. And this is the inverse of the encryption. So like we said yesterday, if I encrypt something and then I decrypt it, I should get the original message back. So the encryption and decryption are inverse functions of each other. Okay, so this is the definition. It's kind of a lot of math, but if you want some intuition, it's, I guess I have to talk about properties first. Okay. And the properties we're looking for are correctness. So it needs to be a permutation, kind of similar to what we said yesterday. It needs to be efficient. So we're looking for fast algorithms, and it needs to be secure. And we'll talk about how it's secure in just a moment. But first, we should talk quickly about intuition. So it's kind of a lot of words and math, but the main intuition for block cipher is it's basically Enigma, but for computers is how I think about it. So if you remember Enigma, the German encryption machine from yesterday, how did you run Enigma? You would take your rotors, the little wheels, you would put them in the machine, you would take them to their correct position, you would take the plug board, you would connect all the wires up. And then once you had the rotors and plug board set up, the key was inputted and fixed, right? There was no more changing of the key. So you put in the key, you're done with the key. And now all you do is you type a plain text letter and you get a ciphertext letter. And you do that over and over again for your whole plain text. So there were 2 inputs, right? The first input was the key. So that was the rotors and the plug board. The second input was the plain text, and the output was the ciphertext. So that was how Enigma worked. So block ciphers are basically the same. Yes. So once you set the key, so in Enigma, once you set the rotor and once you set the plug board, the key is set. You're not changing the key anymore. All you're doing is mapping plaintext to ciphertext. So block ciphers have 2 inputs, but it's basically the same idea. You set the key. So the key input is the same every single time because the key is set. And once you set the key, you can map all of your plain text to all of your ciphertexts. And you can also map all of your ciphertexts to all of your plain text with the decryption function. So block ciphers are basically Enigma, but for computers. And in Enigma, if you don't know the rotor and you don't know the plugboard settings, so if you don't know the key, then the machine doesn't work. You can't encrypt or decrypt. You know the algorithm, you can see the machine, but you don't know how to encrypt or decrypt. And block ciphers are the same. If I don't know the key, I know the algorithm, I know how the algorithm works, but because I don't have the input of the key, I can't encrypt my own messages and I can't decrypt my own messages. Okay, so that's the intuition. I'll pause quickly if anyone has questions. Okay, so again, there were 3 properties we're looking for in block ciphers. So the first one is it has to be correct. And we talked about this a little bit yesterday, but basically block ciphers have to be a permutation on n-bit strings. Sometimes it's called a bijective function. And all this means is every input has exactly one unique output. So I can't have 2 inputs mapping to the same output. And we talked about this yesterday. The reason why we can't have 2 inputs mapping to the same output is because let's say I encrypt 1, 0 and I get 1, 1. Then I encrypt 1, 1 and I also get 1, 1. Well, now we have a problem because if someone gave me the ciphertext 1, 1, how do I decrypt it? Does it decrypt to 1, 0? Does it decrypt to 1, 1? I don't know because both of those are possible. So on the left, this can't be a block cipher because I can't decrypt. It doesn't work. On the right, this is a valid block cipher for 2-bit strings because every input maps to exactly one output. So for example, if I get the ciphertext 1, 0, I can decrypt it and it always decrypts to 1, 1. So there's no ambiguity. So to be correct, it has to be bijective. Okay. Then the second property we're looking for is security. So a secure block cipher, the way we measure security is we say it behaves like a randomly chosen permutation from the set of all permutations on n-bit strings. That's a lot of mathy words, so I guess we'll break it down. So a random permutation is just a permutation where I take every input and I map it to one of the outputs randomly. So for example, maybe if this is a random permutation, I would say 0, 0 maps to one of the 4 and I just randomly chose this one. So I flipped a coin and I chose this one. Then we say 0, 1, which one does this map to? Well, I'll just pick one of the 4 on the right at random, and maybe I chose this one. And then 1, 0, which one does this map to? Again, I'll choose randomly and I'll get 0, 1, and then 1, 1 will map to 1, 1. So I chose these arrows at random. I did choose them so that we would never have 2 arrows pointing at the same ciphertext because it is a permutation, but how the arrows were arranged, I chose it randomly. So you can think of a random permutation as I just drew the arrows at random, and then once I finish drawing them, this is the permutation. So that's a random permutation. And what we're saying is that if the block cipher is secure, then you can't tell whether it's a block cipher or a random permutation. They look the same. So one way to formalize this is to use a game. So if you're Eve, we're going to give you 2 boxes. So they're black boxes. You can put in some plain text input and get some chosen or ciphertext output. And Eve can do this as much as she wants. So she can play with both boxes. Both of them, if you give it some input, it will give you the output. So one of the boxes is a randomly chosen permutation. So we just drew the arrows at random and then gave it to Eve. And when Eve puts in some input, it will follow the random arrow and then give you the output. The other one is a block cipher with a randomly chosen key K. So again, remember the block cipher, once you fix the key, right? Once you choose the key, it's a function that maps plain text to ciphertext. The key input is fixed, it's the same every time. And then you can map every plain text to every ciphertext. So what we're saying is one of these is a randomly chosen permutation. The other one is a block cipher with a fixed key K. So both of them, she can play with it as much as she wants. She can give it inputs, she'll see the outputs. But if we asked her to guess which of these is the random permutation, and which of these is the block cipher, she can't guess with probability greater than 1/2. So she's just guessing. So for example, down here, right, these two, both of these are permutations, and Eve can look at them, but she will have no idea which one came from a block cipher algorithm and which one came from a random permutation. So she won't know. And if that's true, then the block cipher is secure. Okay, any questions? Okay. Well, one thing you can try on a block cipher, and we talked about this a little bit yesterday, is a brute force attack. So maybe I get some ciphertext, and remember how yesterday in the Caesar cipher, I just tried every single key until I found one that looks like English? Well, maybe I can try that on block ciphers too, right? How about I get some ciphertext, and I know the block cipher algorithm because of Kirchhoff's principle. I know the algorithm. So what if I just try every single key? Does that work? Can I do that? Well, in modern block ciphers, and we'll talk about this a bit later, the keys tend to be 128 bits long. So that means I have to try 2 to the 128 possibilities. So how big is 2 to the 128? Well, I can do some back of the envelope calculations, and I think we'll skip over some of these because it's not that interesting. But basically, 2 to the 128 is approximately 10 to the 39. So it's 1 with 39 zeros. That's a really big number. So it's so big that let's say I have some new genius quantum whatever hardware. This hardware lets me try 1 billion keys in 1 billionth of a second. That's really fast, right? In 1 billionth of a second, I can try 1 billion different keys. So if I do that, that's 10 to the 18 keys per second. I don't even know if any modern computer can do that, but suppose we had some magic computer that could do this. If so, how long would I take to brute force this key? So we're using magical miracle hardware. How long would it take? Well, it would take 10 to the 21 seconds. And if I do some more math, that's something like 30 trillion years, which I think by the time you're done, the solar system will stop existing or the sun will burn out or something. So we're talking like astronomical sizes here. So galaxy sized, solar system sized, length of the universe sized attacks. So by the time you figured out what the 128-bit key is, you probably no longer exist. The Earth doesn't exist anymore. None of this exists anymore because it's just taken too long. So the takeaway here is just you can try brute forcing a 128-bit key, but good luck because you will not finish. And someone asked, well, what if I run it parallel? Well, you could run it parallel, but again, the number is just too astronomical. So, if I ran 2 of these magic machines in parallel, maybe I'm down to 15 trillion years, but it's still kind of like good luck. If you wanted to get this down to a reasonable number, you would need something like 1 trillion machines. But I don't know any real world manufacturer that can give you 1 trillion machines. So yeah, you can parallelize, but it's still mind boggling. So there's just no way to get this number down in any reasonable amount of time. And someone also pointed out that if you try brute forcing, it's possible that because there are just so many keys, like that's a lot of keys, it's possible that multiple different keys give you an English message, and I can't even figure out which one is which. So that's a good point too. And someone did bring up parallelism, so let's try thinking about that. But let's also make the problem a little bit harder. So let's say I have a 256-bit key, and I want to try using parallelism to make my attack feasible. Okay, so remember our little genius machine from before that could compute 1 billion keys in 1 billionth of a second? Let's say I have one of those machines, right? Well, that's not enough. Let's say if I wanted to finish this attack, I would need something like 10 to the 52 of those machines from before. So that one little machine, I don't think it exists. It would be like a magical machine. But if I had one of those, I would need 10 to the 52 of them to do a 256-bit key brute force. If one of them was 1 cubic millimeter, which is very small, this would take 10 to the 43 cubic meters, which is like a trillion zillion suns. So the volume of it is just ridiculous. There's just no way to think about these numbers because they're so gigantic. So even if I had parallelism and I tried it, it just is not going to happen. So the takeaway is you can do all these fancy numbers. The numbers you'll get are always going to be things like number of grains of sand in the universe or number of atoms in your body or whatever. They're just too big to even think about. So brute force attacks on modern block ciphers just can't be done. So if you have a 256-bit key or 128-bit key, it's not happening. Yeah, so someone asked, what's the probability that I randomly get a correctly formatted JSON with the wrong information if I had random strings? That's a good question. I think you would have to crunch some numbers because JSON's a pretty specific format. But my guess is it would not be a very high probability because JSON is pretty carefully formatted. But yeah, the takeaway here is just brute force attacks are not happening with block ciphers. The key is just too big. Okay. So I think we hammered that enough, and we might remind you of it a few times later. But let's talk really quickly about efficiency. You don't have to worry about it too much because we're not going to talk too much about implementation. But basically, block ciphers use lots of XORing and bit shifting. So the operations are very cheap and very fast on modern processors. And a lot of modern CPUs even create dedicated support for block ciphers. So the hardware itself is wired, like the wires connect in a very special way to make block ciphers faster. So CPUs are designed to make block ciphers fast because modern computers have to encrypt and decrypt very often. So all you really have to know about efficiency is make it fast and use cheap operations like XOR and bit shift to do block ciphers. Okay, so really quickly, we'll give you a history of how block ciphers came to be and how people designed them. So the very first one that happened was DES, Data Encryption Standard. This happened in the late 1970s. The block size N was 64, so you take in a 64-bit input and return a 64-bit output. The key was 56 bits long, and the NSA, the National Security Administration, influenced two parts of DES. So while DES was being designed by researchers, the NSA came in and said, you know this part of the algorithm? You should probably do it this way. And they didn't tell us why. So everyone was like, why are you telling us to fix the algorithm like this? And nobody could figure out why they were doing it. But like, is it because the NSA found a backdoor and they want to hack us? It's not clear. But I guess people just accepted it, thinking that the NSA had some idea. So it was accepted. The NSA also changed the key size. It used to be 64 bits, but it dropped to 56 bits. So why could this be? Well, in 1970s, 64 bits was considered infeasible, or very hard. But 56 bits was considered more feasible and more possible, I guess, if that's a word. So another thing that was kind of weird and everyone was like, what are you doing here? But the NSA did make the key size a little bit smaller so that an average person probably couldn't brute force, but maybe a very big security organization could. So that's what happened with DES. So if you're wondering what happened there, well, DES turned out to be pretty secure. So people researched it for 40 years to try to figure out are there any attacks on it, and nobody could really find any. So presumably the attack or the algorithm was secure and it was indistinguishable from random. Some people might be wondering what the NSA actually did. So about a decade later, people found an attack that almost worked. So the attack could have broken DES, but somebody switched something in the original DES to make this attack not work. And who was it? Oh, it was the NSA. So I guess in this case, I don't know why they did it this way or why they didn't tell us about it, but it turns out the NSA changing those workings, maybe on purpose, maybe by accident, defended it against an attack that we found out about 10 years later. So thanks, NSA. I don't know. But in modern days, if you use DES, it's not going to work because 56-bit keys are very easily brute forced in modern day with modern day computers. So 128 bits, probably not, but because this was an older algorithm with 56-bit keys, you could brute force it. Okay. The next algorithm we'll talk about is AES. So this is the one that's used today. A really brief history is in 1997, DES was getting pretty outdated. So the National Institute of Standards and Technology in the United States said, let's find a new block cipher. So they asked all the security people to submit their designs, and they had a little competition to pick the new one. And the reason why we bring this up is because there were 5 finalists, and one of them actually came from our own 161 instructor and Berkeley professor, David Wagner. So shout out to him. And that design was called Twofish. So there were 5 finalists, and they did some performance evaluation, which you can read about yourself. But basically, based on performance and security, the one that was chosen was called Reindel. I think that was the name of the inventor. So today, the modern advanced encryption standard AES block cipher is the Reindel design. So sometimes you hear it called Reindel, but most people just call it AES because that's the competition that it won. And almost all modern computers, if you encrypt, you use AES. So AES uses 128-bit key size. Like we said earlier, this size is good enough to defend against basically anything but maybe aliens. And there are versions with 192-bit keys and 256-bit keys. So if you're super paranoid and you think, well, what if someone after the life of the solar system finds out the love letters I was sending? Well, okay, fair enough. But then you can use even bigger keys to stop people after the solar system from learning about your letters. So if you're really paranoid, you can use bigger keys, but for most purposes, 128-bit is good. Sometimes you see it written like this to denote 128-bit keys, 192-bit keys, 256-bit keys, but yeah. The block size is 128-bit keys or 128 bits no matter what. So you always input 128, output 128. The algorithm itself is out of scope, so don't worry about it too much, but there is a fun comic that shows you how it works. But basically, it's just a lot of shuffling, and it shuffles things in very unpredictable ways, so the output can't be met to the input. So it does a lot of shuffling that can be reversed if you know the key, but if you don't know the key, the output just looks random to you. So one interesting thing about AES, though, is that there's no formal proof that it's secure. So nobody has actually figured out a mathematical proof that you cannot distinguish it from a random permutation. But it's been 20 years. Security researchers have tried again and again and again to break it, but nobody has actually succeeded. So our assumption is AES is secure because it's been 20 years and the crypto experts have tried over and over again. The NSA has probably tried it too, and nobody can figure it out. And even NSA uses AES. So if the NSA had broken an AES, they probably would not use it themselves. So that's another reason to maybe be confident that AES is secure. Okay. Someone asked about some different symmetric key ciphers. So we'll talk about some different ones later, but maybe Nicholas can field that in chat. Okay. So takeaway, all you have to know is that AES is the modern block cipher and that the standard key size 128 is good enough to prevent brute force attacks. So you cannot brute force 128-bit keys. Okay. Back into non-story content. So remember yesterday we talked about NCPA security as a good definition. It said, in our threat model, considering the attackers we're going to face, this scheme is confidential. So our block cipher is NCPA secure. Does anyone think yes, think no? And we can also walk through it if no one has any ideas. Someone said yes. Okay, so maybe yes. So let's see. And someone said yes because it resembles a random permutation. So that might be true. So let's think about this adversary. So here comes Eve. And Eve is going to try to face off against Alice from before. Eve is going to send two different messages, M0 and M1. So she sends two messages off. So she's not going to use this first phase. She doesn't need it. She'll just send two messages off to Alice. Alice is going to randomly encrypt one with the block cipher because that's the algorithm we're thinking about. So Eve gets either encryption of M0 or encryption of M1. So which one did she get back? Well, now she has to guess, right? But she can also use this second query phase to help her. So is there any strategy she can use down here to maybe help her learn about the block cipher? And remember, there's no limits on what she can encrypt. So whatever she asks Alice to encrypt, so whatever Eve sends here for Alice to encrypt, Alice will always encrypt it and give it back to Eve, no matter what it is. So what's something that Eve could ask Alice to encrypt here that might help her? Any thoughts? Remember, there's no limit, so you can be creative. Or be a little bit cheeky or try the obvious thing. I don't know. You could try an empty message, but remember the block cipher does have to be 128 bits long. So it does have to be, there's no such thing as like a 0-bit message. But you could try, someone said, what if I just asked Alice to encrypt M0 again or M1 again, right? There's nothing that says I can't do that. there's no rules or exceptions that say you can't ask Alice to re-encrypt the same thing twice. So let's do that. So Eve is going to say, you encrypt M0 for me again, right? And Alice will give you the encryption of M0. So what you can do is you can say, well, if the encryption of M0 matches what I got earlier, then you encrypted M0. If the encryption doesn't match, then you encrypted M1. Right? So it's kind of cheeky. It's like, is that even allowed? And it turns out it is allowed. And because it's allowed, you can win the NCPA game with probability 1. So block ciphers are not NCPA secure. The reason being that I can break the scheme by just asking Eve to re-encrypt the message, and I'll get the same thing back. So seeing it for the first time is definitely kind of, it makes you think, like, why was NCPA designed like this? This seems kind of stupid. Like, why would I even design a game like this if I can just break it by asking Eve to re-encrypt the same thing? So there's actually a good reason for this. The reason why is because block ciphers are deterministic. So a scheme that's deterministic means that if I encrypt the same thing twice, I get the same output twice. So you're actually leaking information. It doesn't seem like it maybe, but it is leaking information, right? I'm leaking the fact that I encrypted the same message twice. So if Alice encrypts the same message 2 times with a block cipher and sends it twice, and you're Eve, what did you learn? You learned that Alice sent the same message twice. If I see different messages, then I learned that Alice is sending different messages. So if a scheme is deterministic, you are actually learning information. And that's why when we were designing the NCPA game, we explicitly designed it so that deterministic schemes fail the NCPA game. I want a scheme that does not leak if I'm sending the same message repeatedly. So that's why this game was designed with this kind of stupid loophole, because this stupid loophole actually is a security vulnerability. If my scheme is deterministic and I send the same thing 10 times and I get the same output 10 times, then Eve will know that as well. So again, the adversary can tell that the same message was encrypted twice, so the scheme is not NCPA secure. So that's the first issue. It doesn't even work. It fails our security standard. The second issue is that block ciphers can only encrypt messages of a fixed size. So for example, AES can only encrypt or decrypt 128-bit messages. So what if I want to encrypt 129 bits? Or what if I want to encrypt 127 bits? I just can't, because AES only limits me to 128-bit messages. So that seems kind of impractical as well. What if I want to encrypt something longer or shorter? So these are the 2 problems we're about to solve next with block cipher chaining modes. So this is the first half of the lecture, and I think I'm making okay time, so maybe we'll take like a 3-minute break. Does anyone have any questions before we go on a 3-minute break? I think someone has their hand raised, so go for it.
My question is, if any algorithm is like bijective, right? So I can take it and then I get to like one output at the end, right?
Mm-hmm.
I can win this game with any algorithm that you do. I can just encrypt one and then I encrypt the other one and I encrypt the same old one again, and I'll tell you which one's which. Right? As long as it's bijective, it has to, like, I can genuinely prove that if it is bijective, it's going to lose that game.
Right. So if it's bijective, kind of by definition, bijective functions are deterministic. If I follow the function twice, I'm going to get the same output twice, because there's like an arrow that I drew, right? So if I follow the arrow twice, I'm going to get the same output twice. So you're right that bijective functions are deterministic, and deterministic functions are not NCPA secure because of what we said here. So does that answer your question? Or maybe I'm not understanding.
No, I got it. Thank you.
Okay, cool. I think someone else has their hand up, so feel free to go for it.
Yeah, I just to clarify, so if you had a block cipher where the key size and the block size were the same, and like say the block cipher was just like a one-time pad, then in order, if you were going to brute force it, you would have to basically XOR the ciphertext with every possible, n bit key, which would then give you every possible n bit plain text, which means that you'd run into every possible message you could possibly send with that, and some of them are going to be gibberish, but you'd also get every single one that would make sense. Right. So in that case, how are any block ciphers any different in how easy they are to like what makes AES better than a one-time pad if they have the same if they have the same key size as block size?
Right. Well, I think the thing is like block ciphers tend to not, the inner workings are more complicated than a one-time pad. So it's not always the case that you'll get every single different output. But I think, maybe Nicholas can correct me here, but I think if the key size is the same as the block cipher output, let me think. I think would you get a subset? No, I think you would get all of them, right?
You'd have to if it was
Right.
bijective, right?
Right. I think you would get all the possible plain text. So I think you're right that if you did brute force it, it would be very hard to tell, even if something was an English message.
Sorry, I tuned out because I was working on some stuff for
No,
project.
don't worry about it.
But
Yeah,
then
but
in that case, what makes what makes them different as long if they're all.
Yeah, I guess the question was what makes block ciphers different from one-time pads, because if you have a block cipher and the key size is the same as the plain text size, then technically if you decrypt it with every possible key, you would get every possible plain text. So
block ciphers aren't required. Let me think about this.
Yeah, I'd have to think about that. We can also just take it offline if you don't have a quick answer.
Would a one-time pad be a block cipher, or?
A one-time pad is not a valid block cipher because you can easily distinguish between, say, just XORing with the key from a pseudorandom permutation, which would be like all inputs are randomly mapped to in a one-to-one correspondence with outputs. And then the key is that it has to be random. With something like XOR, the inputs are predictably mapped to outputs, and so they're not random. Does that kind of make sense?
Okay, yeah. All right.
So I'm not sure if I guess both block ciphers, you can, I guess a one-time pad is a bijective function. It will permute, but it's not a random permutation. And we want that randomness in order to actually be secure. Yeah.
Okay. Yeah, maybe looking at block cipher chaining will help, but I'm not too sure. Okay. If there's nothing else, or time is getting a little bit short, should we just take a 2-minute break? We went from 5 to 3 to 2. But I think 2 minutes is fine. Okay, so we'll be back at.
You can say we've already been on 3 minutes of break and we've just been chatting about random things, but yeah.
Okay. So I guess we'll just keep going. Sure.
Well, let's give it 2 minutes just so we can.
Okay. I should pause the recording now.
Sure. Yeah, we'll come back at.
Okay, I think we're back. So let's talk about block cipher modes of operation. It's halfway through the lecture, so you don't get another woo. You have to wait till tomorrow for that. Okay, so the first thing we're going to do is try and design some block cipher chaining modes together. So here we go. So here's an AES block. It's the same as before. Remember, it takes a plain text, takes a key, outputs a ciphertext. So we've already seen this for the first part of the lecture. But remember, the problem was that this only can encrypt 128-bit messages. So the challenge today is, how do we use AES to encrypt a longer message? So let's say I have a message that's 256 bits long, but it doesn't fit in this one AES block. So what's the simplest thing I can do to maybe solve this? Anyone have ideas? So I have a message that's 256 bits long, and I want to use AES. Someone said more blocks. So yeah, pretty much, right? That's the simplest thing I can do is just use AES twice. So I'll take the first 128 bits and encrypt it with this block, and then take the second 128 bits and encrypt it again. And my output is just the encryption of the first 128, then the encryption of the second 128 bits. And if I want to decrypt, I just decrypt both blocks separately, right? So seems simple enough. One thing to note is that we're going to use the same key for both block cipher blocks. And the reason why is because, remember yesterday we talked about how one-time pads are not practical because the keys are so long. So if I had used a different key for every block here, I would be back to my one-time pad problem where I need long keys for long messages, which is what I don't want. I want one key that's short and works for very long messages is what I'm looking for. So we are going to just use one symmetric key for every block cipher in this case. Okay, so that's it. You just designed your first block cipher mode. Congratulations. And it's called electronic codebook mode. And it basically is it's the most basic thing you can do. You just take your plaintext, split it into blocks, and encrypt every single block separately with the same key. Seems simple enough. Problem is, it's not that secure. So why is AES ECB not NCPA secure? So why do we not even have to go through the whole proof from before? So in one word, why is this not NCPA secure? So why did I not solve the security problem? I guess maybe in the interest of time. Yeah, deterministic, right? It's the same thing as before, just I used more blocks. But again, if I encrypt the same thing 5 times, I'm going to get the same output 5 times. So I'm still leaking the fact that I encrypted the same thing twice. So because ECB is deterministic, it's not NCPA secure. So I still haven't solved my security problem. So as an example, this is kind of the classic example we have you take away from this class, but here's a penguin. It's the Linux penguin. I think it's called Tux, but we're going to try to encrypt the penguin with ECB mode. So I'm going to take every pixel of the penguin. So here's a pixel, here's another pixel, every little dot on the penguin, and I'm going to encrypt the pixel with ECB mode. So the pixel itself can be, decomposed into bits, and then I'll encrypt the bits with ECB mode and see what happens. So here's the encrypted penguin. Can you kind of see the penguin still? You can still see the penguin, right? The problem here is that ECB is deterministic. So if I encrypt 2 bits with the same color, or 2 little pixels with the same color, the output is also the same color. So I encrypted it, but I can still see the penguin. Oops. So maybe 10 years from now, when you're thinking about encryption modes, if you see one that's deterministic, just think about the penguin and the fact that you can still see it. And that's a good reason why ECB mode is not NCPA secure. So we leaked information. We leaked the fact that this was a penguin because ECB is deterministic. So that's the penguin. So let's try to do a little bit better than ECB mode. So again, here's ECB mode. It's not NCPA secure because it's deterministic. So like we said before, you can say the penguin, not deterministic. So let's try to fix that. So the way we're going to fix deterministic schemes is we're going to add a little bit of randomness to it. So let's mix in some random values. So here we go. Here's a random value. It's called the initialization vector, or IV. And this value is going to be different for every encryption. So for every encryption, I'm going to just randomly pick a new initialization vector. And before I encrypt the block, I'm going to XOR it with the initialization vector and then encrypt it. And that's my ciphertext. Okay, so now if I encrypt the same plaintext 5 times, each time I'm going to XOR it with a different random value and then pass it into encryption. So my output is going to be 5 different random values. So I no longer have the penguin problem where if I encrypt the same thing twice, I get the same output twice because the IV is here to rescue me. So that's good, but that doesn't fix the fact that these blocks still are deterministic. I only fixed my first block. So how am I going to fix this? Well, I could put an IV in front of every single block, but randomness, as you might remember from yesterday, is kind of expensive, so I don't want to do that. But I'm going to notice that this ciphertext down here, this is already deterministic or random. It's not deterministic anymore because I have some randomness here and it got fed over here. So this is random. Well, if this is random, then I can use this as an IV for the next block because it's just some random value that I can't figure out, right? So if this is some random value, I'll pass it here. Then this output will also be random. And if this output is random, then I'll just chain it to the next block So this plain text is XORed with some random stuff and then encrypted. So this output is also random. Right? So the idea here was basically, the first thing I did was put some randomness here, and then that made my first block random. Then I'll take my first block output randomness, put it in my second block. So now this is random. Then I'll take this and put it here, and this is random now. And I'll just keep doing this for every single block. And if I do this, then we've designed our second block cipher mode, which is called CBC mode. And that stands for cipher block chaining, because I'm chaining the blocks together. So if you want to write this as an equation, I can write it like this. The ith block of ciphertext is the encryption of the ith block of the message XORed with the previous block of ciphertext. So let's take a look at that. So this is the ith block of ciphertext. This is the encryption, right? We passed it through the encryption of the XOR of the plain text and the previous ciphertext. So here's the plain text, here's the previous ciphertext. I XOR them together, and then I encrypt it, and I get the ciphertext. So the equation is just the picture, but in math. And one kind of notation thing to help us out is just that C0 will be the IV. So this just makes our first block work. So C1 is equal to the encryption of M1 XOR C0, and C0 is the IV. That just makes our life a little easier. Okay, so this is block cipher encryption. Now we have to figure out, does it work? Does it decrypt, right? The first thing we need is correctness. So does it decrypt? Well, it kind of does. So here's how we decrypt. So if you stare at the diagram and squint a little bit, so if you like pictures, stick around for this one. If you don't like pictures, stick around for the next slide. But if you like pictures, what I can do is I can take a look at, well, here's my ciphertext. If I want to decrypt it, the first thing I have to do is push it backwards into the block cipher. So I have to decrypt the ciphertext, right? So that's what I did here. I take the ciphertext and I push it through block cipher decryption. So that's the first thing I do. But then once I push it through the block cipher decryption, it's still XORed with the previous block of ciphertext, right? So I also have to cancel out the previous block of ciphertext. So that's what I'm going to do. I'm going to XOR again with the previous ciphertext to cancel it out, and then I get plain text back. So that's what I did here. I pass it through the decryption to cancel out the encryption. Then I XOR it with the previous ciphertext to cancel out the ciphertext, and I get my plain text back. So if you squint a little bit, you can see that basically all I did was take this diagram and just flip it upside down, and I got this one. So that's basically all I did. So this is just, the decryption is just the upside down of the encryption. Okay, so if you like pictures, you can take a look at this one and turn your head upside down and you get this. If you don't like pictures and you like equations, then here's the equation version. So now we're just doing algebra. So if you like algebra, this one's for you. Here's my definition of encryption. We saw this from before. I want to solve for M because I want to figure out how to decrypt. So I'm going to try to solve this equation for M. So here we go. So the first thing I'm going to do is I want to get rid of the encryption function. So how do I do that? I'm going to decrypt both sides. So if you remember your algebra, I'm just decrypting the left side and the right side. So the left side becomes decryption of ciphertext. The right side becomes decryption of this thing. While decryption and encryption are opposites of each other, they're inverses. So they cancel out. So D and E cancel, and I get this. So this is my new equation. But I'm still not solving for Mi yet because I still have the C of I minus 1 to cancel out. So how do I do that? I use my XOR cancel out property to do that. So I XOR this with C sub I minus 1 on both sides. So left-hand side, C sub I minus 1, right-hand side, C sub I minus 1. Those cancel out. And now I solve for Mi. So Mi is equal to the previous block of ciphertext XORed with the decryption of the ciphertext. So it's exactly what we saw from the picture. You take your ciphertext, push it through decryption, and then XOR it with the previous block to cancel it out. So if you like pictures, use the last slide. If you like equations, use this one. It's the same thing. Really quickly, we can talk about efficiency too. We can say, can you parallelize it? So if I have a 10,000 block message, then it would be nice if I can encrypt all 10,000 at the same time. That would be nice, but not going to happen because I have to wait for each block to finish. So I get the ciphertext output and I can chain it to the next block. So unfortunately, I can't parallelize because I have to wait for every block to finish. Sad. But I can parallelize decryption because all I have to do in decryption is, well, I have to pass the ciphertext through decryption and then the XOR happens down here. But notice that the input to my block cipher is always just the ciphertext. So I can do all the decryption in parallel. So I can decrypt in parallel, but I can't encrypt in parallel. One other thing to notice for CBC mode is padding. So far we've talked about messages that are 128 bits or 256 bits, but what if my message is not exactly a multiple of 128? So what if my message is 129 bits? Well, what do I do now? Well, notice that CBC doesn't work if I have a message that's not a multiple of the block size, right? Let's say I have a message that's like 300, which is not a multiple of 128 bits. Well, then I'll fill this up, and then I'll kind of fill half of this up. But if I only fill half of this up, how do I pass that through the block cipher? Doesn't work, right? Because block ciphers take 128 bits, but this is only going to be half. It's not 128. It'll be like 60 bits or something. So AES CBC doesn't actually work if my plaintext isn't a multiple block size. Well, that's kind of annoying, but there is a way to fix it, and all you have to do is just pad the message. So just add some dummy bytes at the end until it's the right length. Right, so just fill it up with some other garbage, and then it's the right length, then I can encrypt it. And then when I decrypt it, I'll just de-pad it, so the other person will just chop off all the garbage at the end until I get the right thing back. So that seems simple enough, but because we're in crypto, it's not always that easy. So it turns out padding is kind of hard. You can't just pad with zeros. You also can't just pad with ones. And in the interest of time, you will see all of this in homework too. So I think we'll skip over for now, but you can come back to look at this or just work through homework too. But basically, padding is kind of a hard problem because there's ambiguities. So you have to be a little bit clever to pad things correctly. Okay. One kind of simple scheme that works is just put the message length in the message. So this message is 300 bytes long. And then when the other person decrypts, they know that, oh, this is a 300 bit or 300 byte message. So they can just keep the relevant parts. So that's one easy way to pad. But there are also more complicated ways that you'll see in homework. Okay. And quickly, we'll talk about security. The actual proof of in-CPA security is out of scope, so we're not going to force you to prove it. But AES CPC, if you use it correctly, is in-CPA secure. But there's one really big assumption you have to make. What's the assumption that you have to make for AES CPC to be in-CPA secure? Does anyone have thoughts? What was the one thing we added to CPC to make it not like ECP mode? IV has to be random, right? The one thing we added was IV, and we told you it was random, but you actually have to make it random for this thing to work, right? You have to make it random, and you can't reuse it. Otherwise, CPC will not be secure. What happens if I do reuse the IV? Well, things start to go wrong, right? If I reuse the same IV every single time, guess what? It's deterministic again, no more in-CPA security. So we said it's random, but you actually have to follow through and make sure that it's random when you're using CPC mode, or else no in-CPA security for you. As an example, I guess the animation kind of messed up, but there you go. Here's 3 block messages. So this one, the first 2 blocks are the same, and the third block is different. And the second message, the first 2 blocks are also the same, and the third block is different. So if I follow this through, and I think you'll do this in discussion as well, but basically what happens is the first block is the same, the IV is the same for both messages. So this first ciphertext block will be identical for both of these, and the attacker will see that the first ciphertext block was identical for both messages. Then I pass it into the second block. These two are also identical. So when I pass these through block cipher, I'll also get the same output here for the second block. Then I go through for the third block, and I pass that through, and this is now different. And I pass this through to the third block, and this one's different. So in short, and you'll see this again in discussion at a slower pace, hopefully, but basically, if I reuse the IV, if the messages are the same, then I'll see that. It's deterministic. But also, if the messages are different, I will actually see if the messages start with the same plaintext blocks up to the first different one. So it does leak personal information about messages is the takeaway here. Okay, so, but let's assume you use it correctly. So I do not reuse the IV, and I use random IVs every time. Here's my penguin, encrypt with CBC mode. That looks great, right? No penguin in sight. I have no idea what this says. So that's great if I do not reuse IVs. If I do reuse IVs, guess which penguin I'm getting? I'm getting the ECP penguin back. But if I don't, then I get this. Okay, so that's our first scheme. Let's take a look at our second scheme. So this one, or I guess that was our second one because we had ECV, which was terrible. Now we have our third scheme. So for this scheme, we're going to think about one-time pads again. So remember last time, one-time pads, take the key, XOR it with the plain text, get your ciphertext. One-time pads are great, right? They're secure if I never reuse the key. That's great. But remember, there was a problem with key generation. So let's try to do a mashup. So we're going to mash up one-time pads with block ciphers, and we're going to get a scheme that's NCPA secure and practical. So mashup time, I guess. So here's our block cipher. If the attacker doesn't know the key, this just looks like random gibberish to the attacker, right? That's what we said about the block cipher being indistinguishable. If I don't know the key, this just looks totally random. So guess what? If this looks random, what if I use this to simulate a one-time pad? So if you squint a little bit, you can think about that, right? This is just some random gibberish. If I use this random gibberish as the key, that can also be a key to my one-time pad. So let's see what that looks like. So instead of just using one, I'm going to use a lot of these. So I get lots of key material. So all of this can be used as a one-time pad because it all looks random. So if the attacker doesn't know the key, this is all random garbage. And so I can use it as a one-time pad key, and that's what I did. So I took some stuff, I encrypted it with a key that the attacker doesn't know. I got a lot of random output, and then I XORed my plain text with my random output to get ciphertext. And this is my mashup of one-time pads and block ciphers. Okay. Now, one last thing that I haven't filled in yet. So it's almost done, but I have to fill in this thing. I haven't filled in my input to the block cipher. So what's the one thing that we're missing in this scheme that we had in CPC mode to make things in CPA secure? We're still missing one thing, right? Randomness, right? We haven't added any randomness yet, but we only have one thing left to fill. So let's just put randomness here. So there you go. Now we have randomness here. And this randomness is going to make sure that the scheme is different every single time. And one other thing I'm going to do is add a counter to every block. So random value 0, random value 1, random value 2. And because I'm ticking the counter for every block, the block cipher encryption will also be different every single time. So the nonce is to add randomness for different encryptions. So if I encrypt something a bunch of times, I'll use different nonces. The counter is just to make sure that within a single encryption, the blocks are all different so that I get a bunch of different one-time pad keys. Okay, so now we designed our next mode, which is CTR or counter mode. It's named that because of the counter right here. One thing to notice is that we called it nonce here, but it's the same as IV and CPC mode, so don't worry about that. But we're basically going to use nonce and IV as synonyms, so that's fine. Okay, so this is CTR mode. I guess one thing I neglected to mention in BC mode and CTR mode is that the nonce and the IV is sent over the insecure channel as well. So the other person has to know what the random value is in order to do the decryption. So that's one thing to keep in mind. Okay, so the IV is public. It's not a secret value. It's just a random value, but it has to be known by the other person to decrypt. And that's what we're going to see here. So again, here's the nonce. And Bob knows the nonce when he receives the message so that he can decrypt. One funky thing to notice about CTR mode is look at the block ciphers. They're using encryption, not decryption. So that's kind of weird, right? I am decrypting CTR mode, but I'm using the encryption function for block ciphers. The reason why we're using encryption here is because if you look at the encryption mode here, the plain text never went through encryption, right? If you see the plain text here, it never went through encryption. The encryption is just for me to generate pad, the one-time pad. So because I never put the plain text through the encryption block, I also don't have to put the plain text through the encryption block to decrypt. So the intuition here is basically the reason why I'm not using the decryption block is because plain text never went through decryption. The encryption is just to give me one-time pad stuff. So I don't know why this just says XOR with, but it should say XOR with ciphertext. So now you know. So essentially what Bob is doing when he receives a message is he takes the nonce, which is public and everyone knows it, uses the nonce and the counters to generate the pad again. So this entire top half is just for generating the pads again. And to regenerate the pad, you use the encryption method. So you go forward to generate the blocks, the pad. Then once you have the pad, you encrypt it with the cipher, or you XOR it with the ciphertext to get the plain text back. So if you squint a little bit, this is just one-time pad. Okay, so here we have one-time pad, but with block ciphers. Okay. A quick note about efficiency. You can parallelize this because notice every block is basically independent. There's no chaining, so you can parallelize. You can also decrypt or parallelize decryption because, again, no chaining. So if you just look at the diagrams, they're all independent blocks. Someone asked, how would the block cipher being a non-random permutation break CBC? I think that's something we can talk about offline because I don't know the answer offhand. A quick note about padding as well. So again, we have to think about what if our message isn't a multiple of the block size? Well, in this case, I'm actually fine. I don't have to pad. The reason why I don't have to pad is because plain text never goes through the block cipher. In CVC mode, plain text went through the block cipher, so it had to be a proper multiple. But in this case, plain text never goes to the block cipher, so I don't even have to worry about padding. If my one-time pad comes out too long, I'll just chop off the last bits of the pad and then just XOR whatever I have left with the plain text. So I don't even have to pad. So that's nice. Well, what about security? Well, again, CTR mode, if you prove it, it's in CPA secure, and the proof is to use the proof from yesterday, which is that one-time pads are secure. But again, we have to assume one thing. What do we have to assume? Random, right? Random is like the theme of this part of the lecture. So again, the nonce or the IV has to be random and it's never reused. Why? Because if I reuse it, guess what? It's not only is it deterministic, which is bad, but it's also like reusing a key in a one-time pad. And we saw what happens if you reuse a key in a one-time pad yesterday. It's pretty bad. So yeah, do not reuse the nonce because if you do, you're basically doing two-time pad, which is not good. Okay. And not only is it bad, it's catastrophic, right? Because you leaked the XOR of the two messages, which is usually enough to deduce the plain text. Okay. So here's our penguin again. If I encrypt with CTR and I use the random nonces every time, the penguin looks like gibberish. So we have finally taught you enough that I can go back way back to yesterday where we talked about how 61A screwed up and became an example forever. Now you actually know what they did. So here's what they did. They used the Python library for AES. Simple enough. Now, this library is not great, but I don't think we'll go into that. Now, they used CTR mode to encrypt their exam. So they used counter mode for encryption, but they didn't specify an IV. So the IV was blank. Okay. Now, their assumption was, well, I don't specify an IV, so the crypto library will give me a random IV so that CTR mode is secure. But the crypto library just defaulted to IV equals 0. Oops. Now what? Now the entire exam was encrypted with the same IV. So every question used the same IV. And what does that mean? That means I'm using a one-time pad twice, which means no security for you. So that was actually what they did. And now you know exactly what they did. So it turns out any CS161 student, if you had taken this class and learned about CTR mode and two-time pads, you could have decrypted the exam and leaked it before it was released. So now they are forever immortalized in this lecture. Who found out? Good question. I think one student reported that the exam had been leaked. I don't know if they were lying or if they were being honest, but because they reported it, everyone looked into it and tried to figure out how it was leaked. And when they were looking into it, Nick, who teaches this class, sometimes looked at the code and was like, wait a minute, did you not use an IV in CTR? And the 61A TAs just had to be like, whoops. And so that's how they found out that the algorithm was busted. But we don't know if any 61A student actually knew enough about encryption to do this. So that will forever be a mystery. Okay, takeaway, do not reuse IVs. So one of those things that we have to yell at you a couple of times, do not reuse IVs or else you will get to join the summer 2020 61A staff in infamy in these slides. Okay. So just to remind you yet again, IVs and nonces are random values they're public, so we don't have to keep them secret. Alice and Bob will share them to each other when they're encrypting and decrypting, but they have to be random, so and never reused. Okay, so I think we hammered that home enough, but here's another slide just to remind you that IVs and nonces are public, so everyone knows them, but they're random and they cannot be reused, or else all the security guarantees that we just figured out are completely busted. So how bad is it if I reuse an IV? Well, it depends, right? In CBC mode, I leaked a little bit of information because I learned that these two messages start with the same blocks. In CTR mode, I learned the XOR of two messages, which is catastrophic. So how bad is it if I reuse an IV? It depends. And you have to think really hard about, wait a minute, if I reuse IV, well, this happens, and then this happens, and then this happens. So you have to think really, really hard about what happens if you reuse IVs. So my recommendation to you is just don't reuse IVs. If you don't reuse IVs, you never have to think about it. If you do reuse IVs, now you're going to have a huge headache because you have to think about, well, if I reuse IVs, then this happens, then this happens, then this happens, and it's a big headache for you. So don't reuse IVs, and you don't have to think about this. If you reuse IVs, then you have to think about this, and your life will be very miserable. I think we just said that. So again, even more attacks happen if you don't reuse the IV, but the attacker can predict future values. Now you have to think even harder, and you have to go grab your pencil and paper and think about attacks. I don't want to do that because I don't like thinking hard if I don't have to. So what are you going to do? You're going to generate a brand new random IV every single time. And if you do that, you never, ever have to think about it again. So generate random IVs and stop thinking about IV reuse. Okay. So you can compare all the different modes of operation. They all work, and which one you want to use is up to you and depends on your needs. So for example, if I want high performance, which one do I use? I probably use CTR because I can parallelize, right? If I want security, which one do I want to use? Well, technically they're both secure, but if I screw up and I reuse the IV, CBC mode only leaks a little bit of information, and CTR mode leaks a lot of information. So if I really cared about security, I would probably pick CBC. And you can analyze these trade-offs when you're thinking about security, about which mode you want. But generally, for performance, use CTR. If you really care about security, CBC is a little bit safer. And again, this is kind of considering human factors, because if someone screws up and doesn't know about IVs because they don't know about how encryption modes work, CBC is safer for them to use, because even if you screw up, you only leak a little bit. But if you use CTR and you screw up, well, everything is gone. Okay. There are some other modes, so these are not the only modes that you'll see. So there are all sorts of trade-offs that you can analyze. You can say, do I have to pad? What happens if I screw up? Can I parallelize? These are all things you have to think about for modes of operation. So we're running short on time, but as an exercise, if you want to practice for exams or anything, there's a mode called CFB. And this one is when you can try analyzing yourself. So how do I decrypt? How do I go from encryption to decryption? How do I pad messages? Do I need to pad messages? What happens if I screw up? Is it terrible? Is it like CTR? Is it like CBC? Can I parallelize? And these are all things you can look at the diagram or look at the equations and think about it yourself. So here are the answers if you need them for later. And the last thing that I think we're going to run short on time, but maybe we'll just do it tomorrow, is that block ciphers don't have integrity and authenticity. We said this yesterday, but just to remind you again, block ciphers are designed for confidentiality, so they do not have integrity and authenticity. If you tamper with the ciphertext, there's no way to detect it because block ciphers are not designed for that. So even if you chain block ciphers together, there's no integrity and no authenticity. So if Mallory, who's the manipulator, comes in and messes with your message, there's no more integrity or authenticity if I only use block ciphers. And there's a whole example, but there's no way it's going to get done in the next 3 minutes. So we'll see if we do it tomorrow or just show it to you in the slides. But yeah, in summary, because I only have 2 minutes left, block ciphers are the first thing we saw today. So a block cipher is a set of functions you can encrypt by inputting a k-bit key and an n-bit plaintext and output n-bit ciphertext. Decryption is the same thing. You input an n-bit key and an n-bit ciphertext and receive an n-bit plaintext. The correctness property is if I fix the key, I have a bijective mapping. So one input to one output so that I can decrypt. And the correctness says if I encrypt and then I decrypt, I get the original message back. Security says if you don't know the key, it looks like a random permutation. So given two boxes, Eve can't figure out which one is which. I can try to brute force block ciphers, but the universe will be gone by the time you're done. In terms of efficiency, use bit shifting and XORs because it's fast. And the modern standard is AES. So if you see AES, that's the modern block cipher. Now, there were some issues with block ciphers. They're not in CPA because they're deterministic. Given the same input, I get the same output. So I can see the penguin, which is bad. And they're limited in length. So the next thing we did was we came up with modes of operation. So the first one was ECB mode, not good because it's deterministic. So I saw the penguin, no good. Then I thought about CPC mode, which was it is in CPA secure, assuming what? Assuming I don't reuse the IV. And I thought about parallelizing, we thought about padding, and we thought about what happens if you reuse the IV. Same with CR mode. Again, it's secure if I don't reuse the nonce. It is parallelizable. You can think about padding. You can think about what happens if I reuse the nonce. And finally, we mentioned briefly that block ciphers do not provide integrity and authenticity because they are not designed to do that. They're designed to secure my messages with confidentiality, but there's no integrity and no authenticity. So that's it for symmetric encryption. And next time, which is tomorrow, we will talk about schemes that provide integrity. And it looks like I made it just in time. Any final questions? And if not, I saw a lot of questions about block ciphers, so we can always stick around and talk about those. But if not, have a good June 30th. I don't know why I said June 30th, as if it's a special day, but yeah, have a good Wednesday, and we will see you all tomorrow. And don't forget to work on project 1 so that the rest of your week isn't too miserable. Yes, end of June. I'm not going to do it. You have to wait till tomorrow to see me do it again.